What is light? What is its nature? Since antiquity, philosophers, mathematicians, astronomers, and physicians have sought a solution to this enigma. For 2.5 centuries, a lively controversy existed between partisans of the wave theory, for whom light is a vibration traveling as a wave, against those of the particle theory, for whom light is a stream of particles. Finally, quantum physics, born at the beginning of the 20th century, reconciled the two hypotheses. According to the nature of its interaction with matter, light may be manifested in the form of waves or in the form of particles, the famous photons. A wave is characterized by a wavelength. A photon possesses energy. But on what scale, over what range? Let's start with Isaac Newton. It is the year 1666. In a room with closed shutters, he works with a small opening to isolate a single ray of sunlight. In the stream of light, he places a glass prism. Via refraction, the light breaks down into a rainbow of colors: red, orange, yellow, green, blue, indigo, violet. In reality, indigo does not exist in the spectrum, but Newton added it for good measure. At that time, the number 7 was thought to be endowed with magical and mysterious properties. 7 colors. Light would remain divided into 7 colors for the entire 18th century, called the Century of Light, since philosophers were convinced they were entering a new age illuminated by reason and science. In 1800, the English astronomer William Herschel placed thermometers in the solar spectrum to measure the temperatures of the different colors. Surprise! Beyond red, where the eye sees nothing, the thermometer kept rising. Herschel had just discovered the first invisible light, infrared. And at the other end, there, the surprise was just as great when, a year later, in 1801, the German chemist Johann Ritter exposed a photographic plaque covered with silver chloride to the solar spectrum. He realized that it reacted considerably beyond violet. There is a second invisible light, ultraviolet. A gradient, a scale, was still lacking. This situation ceased to be in 1801 as well, when the English doctor Thomas Young interpreted colors as a manifestation of light's wavelengths. His famous experiment with fringes of interference permitted him to measure the wavelengths in question, which are the size of microns, thousands of millimeters. In 1885, the German physician Heinrich Hertz sought to experimentally verify Maxwell's electromagnetic theory and to popularize it, since it was still poorly understood. He passed a high-tension current through an electric circuit of breakers, 2 small metal spheres placed a few millimeters apart. The charges accumulated in the circuit until a spark jumped. Hertz observed that another spark jumped simultaneously several meters away in an antenna in the shape of a loop. Energy had been transmitted from one circuit to the other without the aid of a conductor wire. What had transported it? Hertz had the answer. It was an electromagnetic wave, a wave that has the same properties as light: reflection, refraction, and a speed of 300,000 kilometers per second. He measured the length of the wave by moving the antenna, around 1 meter. Thus, the spectrum was added to with Hertzian waves, later called radio waves, when the first radio sets appeared. In 1895, the German physician Wilhelm Conrad Röntgen studied an electric current passing through a bulb in which the air was at low pressure. He realized that the bulb produced rays capable of penetrating boxes, bags, suitcases, even the human body. He named them X-rays, rays because they occur in straight lines like light, and X because he did not know their nature. Despite this doubt, X-rays were immediately used in medicine for radiography, but remained mysterious because no optical instrument was capable of reflecting them, focusing them, dispersing them, or even diffracting them. It was only in 1912 that the German physician Max von Laue experimentally succeeded in obtaining the diffraction of X-rays with a crystal. They are electromagnetic waves, but with extremely short wavelengths located beyond the ultraviolet spectrum. That's not all. There is a ray with an even shorter wavelength. Its discovery involved 4 people. Henri Becquerel, who discovered radioactivity in 1896, Marie Curie, who isolated radium in 1898, and Paul Villard and Ernst Rutherford, who showed in 1900 that radioactivity has 3 types: alpha, beta, and gamma. Rutherford only established the electromagnetic nature of gamma rays in 1914 when he observed their diffraction by crystalline surfaces. The electromagnetic spectrum was now nearly complete, but there was still a hazy border between radio waves and infrared. This would be cleared up during the 1940s with the identification of microwaves. During the Second World War, the English developed radar to detect German bombers at long distances. Radar functions on the principle of the reflection of electromagnetic waves with the wavelengths ranging from 30 meters to 10 centimeters, from radio waves to microwaves. During the 1950s, American engineers realized that microwave radar heated objects located close by. That is how a military device gave rise to a cooking method that is very common today. Thus, it took almost 3 centuries to discover the entire range of electromagnetic radiation in all its types of light and all its sizes. Our eyes can only see an infinitesimal part. We're almost blind. Fortunately, we have invented instruments to make up for our eyes' lack of sensitivity. Today, the development of ultrasensitive detectors allows us to capture invisible light, to translate it, and to see its effects. Light has become a marvelous exploration tool. Exploration of the universe, which contains all wavelengths. Astronomy satellites transmit not an overall image of the sky, but rather a series of images for each wavelength, which allows us to create a very precise map of the cosmos and the different objects it contains. Dust clouds, visible and invisible stars, galaxies, neutron stars, black holes, supernovas, and more. Exploration of the matter, lit in different wavelengths. This is done with more and more high-performance instruments, such as sources of synchrotron light. Soleil, the new French synchrotron source, is capable of emitting all types of light, from infrared to X-rays, with exceptional brilliance. Thanks to light, all types of light, today we can see more clearly than ever. We see better, farther, more closely. We are progressively gaining understanding of the world around us.